Decision tree examples. Let's understand decision tree by looking at some examples. The example illustrates the splitting of attributes with respect to the adjacent training data. While using the training data, you can observe that when refund is yes, then cheat is no. If not, check marital status. If marital status is married, then cheat is no. Next, check for taxable income, and if that is less than $80,000, then cheat is again no, else cheat is yes. So, from this example, you can observe that decision is made at each node of the tree or other condition is being checked to make a decision more accurate. Now, look at a weather example by forming a decision tree to check if a cricket match will be played or not based on the climatic conditions. The given diagram illustrates a learned decision tree. You can see that each node represents an attribute or a feature, and the branch from each node represents the outcome of that node. Finally, it's the leaves of the tree where the final decision is made. Internal nodes can test the value of a feature against a threshold if the features are continuous. So in the given diagram, if the weather is cloudy, the playable condition is yes. Else, check the weather for other conditions, that is either sunny or rainy. Check if the condition is sunny. If the condition being sunny is true and humidity is normal, the playable condition is yes, else playable condition is no. Now check if the weather is rainy. So if the weather is rainy and if the wind is weak, the playable condition is yes, else payable condition is no. Let's try to understand the formation of decision tree. Decision tree formation depends on two things. First is entropy. Entropy measures the impurity of a collection of examples. It depends on the distribution of the random variable. Entropy, in general, measures the amount of information in a random variable. Second is information gain. Information gain is the expected reduction in entropy caused by partitioning the examples on an attribute. The effectiveness of the attribute in classifying training data is directly proportional to information gain. Information gain can be defined as entropy of parent node, average entropy of child node. Choosing the classifier. The attribute with the highest information gain is selected as the splitting attribute or classifier. The information gain is calculated upon the decrease in entropy when a data set is split on an attribute. Constructing a decision tree is all about finding the attribute that returns the highest information gain. Step 1, calculate entropy of the target. Step 2, then split the data set on the different attributes. Calculate the entropy for each branch and then add it proportionally in order to get total entropy for the split. Subtract the resulting entropy from the entropy before the split. The final result is the formation gain, that is the measure of the decrease in entropy. Step 3, now choose the attribute with the largest information gain as the decision node. Divide the data set by its branches and repeat the same process on every branch. Step 4, a branch with entropy of 0 is a leaf node, and a branch with entropy greater than 0 needs further splitting. Step 5, the algorithm iterates on the non-leaf branches until all the nodes become the leaf node that cannot be further split. Following Step 5 of the algorithm discussed, the attributes within Outlook are further split with respect to their gains. Working on Outlook equals sunny node. Gain of S sunny, humidity is equal to 0.970 minus 3 over 5 into 0.0 minus 2 over 5 into 0.0 is equal to 0.970. Gain of S sunny wind is equal to 0.970 minus 2 over 5 into 1.0 minus 3.5 into 0.918 is equal to 0.019. Gain of S sunny temp is equal to 0.970 minus 2 over 5 into 0.0 minus 2 over 5 into 1.0 minus 1 over 5 into 0.0 is equal to 0.570. Humidity provides the best prediction for the target. For each possible value of humidity, you can add a successor to the tree. Finally, you arrive at leaf nodes with a strong decision. Look at the diagram. Here, decisions are denoted by D1, D2, D3, and so on, where D1, D2, D6, D8, D14 are non-playable conditions, and D3, D4, D5, D7, D9, D10, D11, D12, D13 are playable conditions. Overfitting of decision trees. How and why does overfitting occur in decision tree algorithms? Overfitting occurs when the learning algorithm continues to develop hypotheses that reduce the training set error at the cost of an increased test set error. The decision tree algorithm continues splitting on attributes until either it classifies all the data points or there are no more attributes to split. As a result, it's liable to making decision trees that overfit by acting very well on the training data at the expense of accuracy in comparison with the entire distribution of data. How can you avoid overfitting? There are, in general, two approaches to avoid overfitting in decision trees. Either allow the tree to grow until it overfits and then prune it, or prevent the tree from growing too deep by stopping it before it perfectly classifies the training data. Let's move ahead and understand other classifier. That is, the random forest classifier. Random forest is a popular and powerful machine learning algorithm. It is a type of ensemble machine learning classification algorithm called bootstrap aggregation or bagging. The bootstrap is a powerful statistical procedure for finding a quantity from a data sample. This is the easiest to understand if the quantity is a descriptive statistic such as mean or standard deviation. It is a technique for reducing the variance of an estimated prediction function. For classification using Bootstrap, a committee of trees each cast a vote for the predicted class. Bagging is the application of the Bootstrap procedure to a high-variance machine learning algorithm type, usually decision tree. When bagging with decision trees, we tend to be less concerned about individual trees overfitting the training data. Random forests are an improvement over bagged decision trees. Random forest changes the algorithm in a way that the subtrees are learned so that the resulting predictions form all of the subtrees have less correlation. It randomly draws data sets with replacement from the training data that has each sample of the same size as the original training set. Let's assume we have a sample of 100 values, x, and we'd like to get an estimate of the mean of the sample. We can directly calculate the mean from the sample as mean times x equals 1 over 100 times sum times x. We know that our sample is small and that our mean has error in it, so we can use the bootstrap procedure to improve the estimate of our mean. 1. Create as many random subsamples of that data set with replacement, which means you can select the same value multiple times. 2. Calculate the mean of each subsample. 3. Calculate the average of all of the collected means and use that as the estimated mean for the data. Now you know that your sample has n examples and m features. So first, we need to extract the subsamples from the huge data set based on the features and examples.